Hi everyone. In today's video, we are going to talk about gas diffusion and how if we have two materials, how they are going to diffuse alongside one another. So to model this, I've drawn out a container here. And in this container, there is going to be liquid water, and there's going to be nitrogen gas that is blowing over top of this. There's also going to be a screen at the top of this container to prevent any pressure differences. And if we think about the real world, let's say we have a water bottle and we leave this water bottle out with the cap off. We know that over time, the water inside is going to evaporate. But why? Normally, we describe this sort of diffusion process using Fick's law. So we write out Fick's law, that is the molar diffusive flux, which is equal to our diffusion constant or diffusive coefficient, which simply just tells us how likely a material is to diffuse. And this is going to be multiplied by our driving force for concentration, or sorry, our driving force for diffusion, which is the derivative of our mole fraction of our component with respect to its area. And this is multiplied by the negative of our total concentration. And this concentration is negative because, as we know, concentration goes from high to low. And if we say that our change in some distance is in the increasing x direction and our concentration gradient is moving in the opposite direction, we have to account for that by using that negative. So if we look at our concentration term, concentration is in units of mole per liter. And if we think about our ideal gas law, that is going to be N for mole over liters, which is our volume, our V term. And if we write out our ideal gas law, PV equals nRT, we can see that N over V, our moles divided by our volume, is equal to the pressure divided by our gas constant R multiplied by the temperature. And we know that if we have a binary mixture with two components, that the concentration of one component plus the concentration of our other component is equal to our total concentration. So if we want to find our total concentration, we need to find the concentration of both of our components and then simply add them together. And like I said, the kind of units or equation for concentration are going to be this pressure over a gas constant multiplied by our temperature. So we're going to have P over RT plus P over RT for our different components. And if we take the sum of those, that is equal to our total concentration. Okay, so let's break down our situation a little bit further to see how our components are interacting with one another. So over here, I have labeled this point at our water level of position 0, and this point at the top of our container as position L. So we can see that we have a change in position going upwards, which we'll label as dz. And then once again, we have our liquid water in our container, as well as our nitrogen gas blowing over top of the container, and our screen that prevents any pressure differences. So we're not going to have any pressure differences, as I just said. So there's not going to be any pressure gradient or any change in pressure that's driving any of this. So there's only going to be this concentration gradient. And we also have this mixture of nitrogen and water up here. So let's start to draw out our trends in our concentration. So if we graph this, we're going to have our position 0 over here and our position L over here. And we're going to be graphing how our concentration is changing with our position. So if we start with our water, we can see that at position 0, our water has its greatest concentration. And then as you move up to position L, that concentration of water goes down. So starting at position 0, the concentration of our water is at the highest. Then as you move towards L, it decreases. So we're going to have this sort of trend right here for our water. Then if we look at our nitrogen, it's the opposite, or it appears to be the opposite. So the nitrogen has its highest concentration at position L and its lowest concentration at position 0. So we're going to have somewhat of the opposite sort of trend going on here. And again, this is for the nitrogen. So based on our graph, we are saying that these trends are moving in the opposite direction. Nitrogen is flowing this way, and water is flowing this way. But if we look up here, as our nitrogen fluxes downwards, once it hits this water right here, it's not going to mix. So as it fluxes down or diffuses down and hits that water, it's not going to mix with that water. It's going to sit on top of that. Therefore, this tells me that we are confusing our diffusion with molar flux. So I want to rewrite Fick's law for a second. So if we look at our Fick's law equation again, that was the molar diffusive flux, which is equal to the negative overall concentration multiplied by our diffusive constant multiplied by the change in mole fraction with respect to position. But there's actually another equation that relates our diffusion and our molar flux. So let's write out this other equation. This other equation says that the molar flux of component 1 is equal to the molar diffusive flux of component 1 plus the mole fraction of component 1 multiplied by the overall molar flux. Now this overall molar flux can be written as the molar flux of component 1 plus the molar flux of component 2. Now we said that this nitrogen has no place to go. It's not going to displace the water, but it will it will move into the water's position once the water is gone, but it's not going to displace the water. So we can say that the molar flux of the nitrogen is 0. And I'm going to describe that by kind of redrawing our example. So we had our water here that was fluxing upwards or diffusing upwards. We had our screen with our nitrogen blowing over top, as well as some nitrogen inside the container. Now this nitrogen wants to counteract this diffusion upwards or this flux upwards of water. The nitrogen is going to have a positive flux, but the overall molar flux is 0. So let's kind of write out an equation that describes that. So we're going to have the molar flux of component 2 is equal to the molar diffusive flux of component 2 plus the mole fraction of component 2. And I'm going to write this in terms of Y just because we're in the vapor phase, multiplied by the overall flux. Now the overall flux we said was N1 plus N2. So this is going to be the molar flux of component 2 is equal to the molar diffusive flux of component 2 plus, sorry, this should be 2, plus the mole fraction of component 2 multiplied by the molar flux of component 1 plus the molar flux of component 2. Like I said, these molar fluxes of component 2 are 0. So this is going to be the molar diffusive flux of component 2 is equal to the negative mole fraction of component 2 multiplied by the molar diffusive flux of component 1. So this kind of tells us that the nitrogen has a positive flux per se, but the total flux of that nitrogen is going to be 0 because we want to counteract the upwards diffusion, the diffusion or the flux in the positive x direction of that water. Because, like I said, the nitrogen has no place to go. Okay, so now we're going to take a look at a more specific example, but it's kind of going to be the same idea. We still have a container with water and our nitrogen flowing over top with our screen that prevents any pressure differences. And then we have a mixture of both our nitrogen and water in the container as well. We are going to be at steady state for this example, and our concentration gradient is going to be what is driving this diffusion. So we're going to have a temperature of 50 degrees Celsius, which if we convert to Kelvin is 323 Kelvin. Our pressure is going to be 1 bar, which is equal to 1.013 times 10 to the 5th Pascal. We're also going to have a vapor length in here. So this length at this water level line is still going to be 0, this position of 0. And up at the top here, this is our vapor length. So this is going to be 1 meter. So we still have our increasing z values going upwards. So this is going to be a change in our z position. If you remember from our previous equations, we also had a diffusion coefficient. And since we're talking about the vapor phase, this diffusion coefficient is kind of a set value. It's an agreed upon value that is 10 to the negative 5th meters squared per second. Now, we're going to be concerned with finding the molar flux of our water. So I'm going to rewrite out our term for the molar flux of our water. We said this was the molar diffusive flux of our water plus the mole fraction of our water. Once again, we're talking about the vapor phase, which is why I'm using y instead of x. And then this was multiplied by the overall molar flux. We said that the overall molar flux was the sum of the individual fluxes. So that was the molar flux of the water plus the molar flux of the nitrogen. And previously we said that the molar flux of the nitrogen was equal to 0 because once again, as that diffuses downward, it has nowhere to go. So that was 0. We can also write out our equation for Fick's law. So that was the molar diffusive flux of water, since we're concerned with our water. And this was equal to the negative overall concentration multiplied by our diffusion coefficient, multiplied by the derivative of the mole fraction of water with respect to our z position. Now we can plug in what we know. So we know our value for n now, and we can plug in a value for our molar diffusive flux of water. So we have the molar flux of water is equal to the negative overall concentration, the diffusion coefficient, the derivative of the mole fraction of water with respect to z, plus our mole fraction of water multiplied by our overall molar flux, which is just the molar flux of water. Now, as we said previously, our concentration was in units of moles per liter, which ended up being N over V if we thought about our ideal gas law, and this was the pressure divided by the gas constant R multiplied by the temperature. Now this is overall concentration, and we are only concerned about water. So we are going to need to find the pressure of just the water, not the pressure of the water and nitrogen. Like I said, we are concerned with finding the pressure for the water. So you can just simply look that up. The pressure for water at 323 Kelvin is equal to 12 times 10 to the negative third pascals. So let's start plugging in what we can into our equation. We have the molar flux of water is equal to the negative concentration, which we found was P, our pressure, over our gas constant R multiplied by the temperature. I'm also going to group in our diffusion coefficient into that. And this is multiplied by the derivative of the mole fraction of our water with respect to our position Z plus the mole fraction of our water multiplied by the molar flux of our water. So now if we move this over to the other side, we will find that this is the mole fraction of the water, the molar flux of the water multiplied by 1 minus the molar flux, the mole fraction of our water. And this is equal to negative the pressure times the diffusion coefficient multiplied by the gas constant R and the temperature T, multiplied by the derivative of the mole fraction of water with respect to Z. Now we can move our dz term over here and our 1 minus our mole fraction over here. So doing that, we'll have the molar flux of water multiplied by dz is equal to negative pressure times the diffusion coefficient divided by our gas constant R and temperature T, multiplied by the derivative of our mole fraction of our water divided by 1 minus the mole fraction of the water. Now this is a separable differential equation that we can solve. We'll note that the molar flux of water as well as negative PD over RT are both constants and can stay out of our integral. And so this becomes the molar flux of our water. The integral of dz, our change in position, this is equal to negative the pressure times the diffusion coefficient divided by our gas constant R multiplied by T, and then the integral of 1 over 1 minus the mole fraction of our water multiplied by the derivative of the mole fraction of our water. Now we want to start discussing our parameters. Over here, we're dealing with our Z, our change in position. And as you can see from up here, our change in position was from 0 to 1 meters. So this is simply going to be from 0 to 1. And then when we think about our mole fraction, we can actually relate that back to our partial pressures. So the mole fraction of water at Z is equal to 0 meters. So right at this interface right here, that is equal to the partial pressure of the water divided by the total pressure of our system. We said the partial pressure of our water was 12 times 10 to the negative third Pascal, and the total pressure of our system was 1 times 10 to the negative fifth Pascal. If you solve for that, you'll find that the mole fraction of water at 0 meters is equal to 0.12. And this is unitless because this is a mole fraction. So this is like our composition. And then we have the mole fraction of our water up at 1 meter, which is at this interface where we have the nitrogen gas, and the mole fraction of the water up there is simply 0. So putting this back into our integral, we have 0.12 down here and 0 up here for a mole fraction. So now we can start solving our integrals. So we're going to have the molar flux of water, and this is multiplied by 1, but I'm not going to put that. This is equal to the negative pressure times the diffusion coefficient divided by our gas constant R and our temperature T. And this is multiplied by the natural log of the absolute value of 1 minus our mole fraction of water, evaluated from 0.12 to 0. I'm going to distribute this negative sign in here. So this is the molar flux of our water, which is equal to our pressure times our diffusion coefficient divided by our gas constant R and our temperature T. This is multiplied by the natural log of the absolute value of our mole fraction of our water minus 1, evaluated from 0.12 to 0. If we put those parameters in, we have the molar flux of water is equal to our pressure, diffusion coefficient divided by gas constant and temperature, multiplied by the natural log of 1 divided by 0.88. Now we can start plugging things in. So we're going to have that the molar flux of our water, which is, of course, what we're solving for, is equal to our pressure, which is of the system, so 1 times 10 to the negative fifth pascals, multiplied by our diffusion coefficient, which we said was 10 to the negative fifth meters squared per second. This is divided by our gas constant, which is 8.314 joules per mole Kelvin. And this is multiplied by our temperature, which is 323 Kelvin. And this is all multiplied by the natural log of 1 divided by 0.88. Now, if you'll recall, because kind of these units are a little bit iffy, like Pascal and Joule, if you put those into SI units, Pascal is equal to kilogram per meter second squared, and Joule is equal to kilogram meter cubed per second squared. So you can plug those in place of Pascal and Joule. And if you do that and you plug in all your numbers into your calculator, you'll find that the molar flux of our water in this scenario is 4.76 times 10 to the negative fifth mole per meter squared second.